Ciao! Summer is almost here, but before the semester is over, I want to share with you a piece of math that looks like magic and is also building our future. What if I told you that the exact same math NASA uses to fold gigantic solar panel into tiny little rockets is also being used by engineers to 3D print every part of an airplane? All of this, it comes down to a shape-shifting trick in complex analysis called conformal mapping. Let's see what it looks. In regular calculus, a function is a graph. But in complex analysis, we cannot draw graph directly because we need 4 dimensions, so we cannot do it. So to visualize function, we think of them as maps. They get points in one complex plane and it spits out points into another one. And a perfectly boring squares get twisted into some random and fascinating figure on the new plane. Look how beautiful this pattern looks. But here's the catch. Even if the overall shapes get wildly distorted, an analytic complex function with a non-zero derivative does something crazy. It preserves angle. If two lines cross at 90 degrees in the original plane, they are wrapped up, they change a lot, but still they intersect at 90 degrees. This is what we call conformal map. But is it always possible to obtain such function? Well, Riemann tells us that any simply connected domain can be conformally mapped to the open unit disk. And this is an existing theorem, so it guarantees the existence, but it doesn't tell anything about the function itself. If you want to be a little bit more concrete, well, you can compute conformal maps for polygons into the unit disk using the so-called Schwarz-Christoffel formula. It has a beautiful integral formula that maps any closed polygon into the unit disk. It's a bit complicated, but at least it's concrete and engineers use it a lot. Enough theory for today though, so let's focus on how engineers use conformal mapping to create amazing things that brings us to the moon and back. So let's say you want to 3D print any part of this airplane. As you can see, everywhere there are curves, right? And you want the structure to be really powerful and strong because you have to fly on it, and you want to be also really light. So how can you do it? Well, usually what engineer does is that, they put honeycomb lattice all over the place. What is an honeycomb lattice is exactly what the bee do to build the hives. They are basically empty, but really, really strong in structure. Now, what's the problem? Is that when you 3D print all of these lattices on a curved surfaces, you have to crop them and chop them. And this is not good for resistance because when you crop it off, the honeycomb lattice lose power and it just cracks. And you don't want these things to crack while you fly on it. So, engineered what they did. Well, they pick up complex analysis, complex function, and they use it. So what they do is that, they pick all this curved part, they conformally map on something flat. On that surface, which is flat, constructing an honeycomb lattice is easy. And then they map it back curved using the conformal map again. In this way, they are able to construct an honeycomb lattice perfectly fit for a curved surfaces, and you can fly safe and sound. Okay? And it's great. But what if we want to do something even bigger than an airplane? NASA frequently needs to send massive flat solar panel into the space, but they need to fit in really small, tiny cylindrical rockets. How do they solve this problem? You won't believe it, but they use origami. Exactly this kind of shapes, nothing else. But you cannot just fold $1 billion solar panel and hope for the best. You need science, and you need math. Researchers use conformal maps to design this complex grains pattern on the solar panel, and then they can fold them precisely into this tiny rocket. By treating the folding lines as mathematical flows lines in the complex plane, they can mathematically map the flat sheet into a twisted buckling up pattern that collapses perfectly inside these rockets. And this is crazy, and it is nice, and is one of the best uses of complex analysis. So look at this. Origami is a beautiful ancient tradition, but for most of us was just a game. But when you inject it with math, it can literally bring us to the moon and back. And this is great. And this is the real power of complex analysis, and is the real power also of playing with math. So that's all I have for you for today. I'll see you next time. Ciao, ciao!